Today I am going to discuss the important formulae to compute the determinants. Firstly, I am going to discuss about the pivot formula. So in this formula, the matrix A will be reduced to a product of two triangular matrices. That is A is equal to LU through the process of LU factorization. We'll discuss the process of LU factorization at the end. So after reducing the matrix A to a product of two triangular matrices, then its determinant gives determinant A is equal to determinant of L into determinant of U. So this is with the help of the property of determinants, which is equal to determinant of L is 1, because all the diagonal elements of the lower triangular matrix are always equal to 1. Hence the product of 1 is 1 into determinant of U, all the product of the principal diagonal elements of U. So which simplifies to the product of pivots. So therefore, whenever we reduce the matrix A to a product of two triangular matrices, then its determinant is always equal to plus or minus product of pivots. So let me take one such example here. Here I have taken an example where A is equal to 1, 4, minus 3, minus 2, 8, 5, 3, 4 and 7, and also I have given the lower triangular matrix of A. So before finding the determinant of A, first I have to get the upper triangular matrix. So let us find the upper triangular matrix of this A through a set of row transformation. So as we know, the upper triangular matrix is, we mean all the entries below the principal diagonals of zeros. So therefore, we have to reduce the elements below the principal diagonal to zeros. These entries, I have highlighted the entries which I have to make it to zeros, that is minus 2, 3 and 4. So let us have a set of row transformation. So all of you are already familiar with the transformations. How? Because in first semester all of you have been studied about the echelon form and how to get the rank of the matrix, etc. So in the same way, so here I will take up a set of transformations to reduce the matrix A to upper triangular form. So what I'll do is, first I will take this entry, I'll make this entry to 0. Next I'll make the first entry of the third row to 0 with the help of a row transformation. I'll make use of the first row to make the entries minus 2 and 3 to 0. So here I have a set of transformation. So first I'll apply the transformation on the second row with the help of the first row, so that here the transformation I'll use as R2. I'm changing the row R2 to R2 times R2 minus 2 times R1, because here we have minus sign. So in order to make this entry to 0, so this element should be of the same set. So here the transformation is R2 minus of minus 2 times of R1. So with this transformation, the second row will changes to 0 minus 2 plus 2 0, then 18 minus of, sorry, 8 minus of minus 2 into 4, which gives 8 plus 8, which is 16, then 5, we'll get here 3 negative signs, so it will become minus. So 5 minus 6, which is minus 1. So after applying this transformation on the second row, we get the new entries in the second row as 0, 16, minus 1. Next, let us make this entry to 0 with the help of again the next set of transformation, which is the second set of transformation here is R3 is equal to R3 minus half of R2. So by saying the elements, you can consider the scalar. Which scalar you have to consider to multiply R2. Okay, since as here, sorry, this one, this one. Since it is 3 and it is 1, so the transformation I have to consider is R3 minus 3 times of R1. R3 minus 3 times of R1. Then we'll get the equivalent matrix as. So we have to write the first and second row as it is. The third row will changes to 3 minus 3, 0. 4 minus 12 minus 8. 7 plus 9. 7 plus 9, that is 16. Okay, so only the next entry will be minus 8. So this I have to make to 0 now. So here, with the help of second row, this is only the possibility. I cannot use the first row now to make this entry to 0. So I can take only the second row, because here we have 0. So I can use only the second row to make this entry to 0. So here what set of transformation I can use? R3, I am changing R3. So R3 to R3 minus half, because this is 16 and this is minus 8. So half of this value with negative times, because here I am using minus. So R3 minus half times R2. So which gives plus 8. So minus 8 plus 8 will be 0. So therefore finally the R3 will give the new entries as 0, 0 and 31 by 2. Since just observe the elements below the principal diagonal, all are zeros. So therefore it is an upper triangular matrix. So now A is reduced to upper triangular matrix. I have L. So now I can find its determinant with the help of the pivot formula. Okay. So which is see A is equal to LU, then applying the determinant, the property of the determinants gives determinant of L into determinant of U. See, all the entries in the lower triangular elements are 1. So the product gives 1 times the product of all the elements of U. So which we call as the pivots. So 1 into 16 into 31 by 2. So which is equal to 248. So this is the alternate method for LU factorization, that is finding the determinant. So without expanding the determinant, we can find the value of the determinant with the help of the pivot formula, that is 248. So one more example I have taken. In the second example also, so I have A and L. Now I have to find U, that is upper triangular matrix, through a set of row transformations. Okay, in the same way you reduce the entries below the principal diagonal to zeros, the entries principal diagonal to zeros. These are the entries 4, 2 and 5. Okay, 4, 2 and 5. Reducing A to upper triangular. So in the same way, making the entries below the principal diagonal to zeros, these entries 4, 5 and 2 with the help of row transformations. Okay, so easily we can identify the transformations, since we are just changing the second row and third row. So the first set of operation is R2 is equal to R2 minus 4R1. This 4 I have to make to 0 with the help of the first row only. So R2 and R3, the elements of R2 and R3 can make to 0 with the help of R1 only. So here I have 4 and here I have 2. So the set of operation is R2 minus 4 times of R1. For the second row it is R3 minus 2 times of R1. Then I will get the new rows, that is R2 and R3, 0, minus 10, minus 9, 0, 1, minus 7. R1 is constant. Okay. Now only I have to make this entry to 0. Okay. So here I can use only the second row, I cannot use the first row, right? So I can use only this entry to make this entry to 0. So the set of operation here is R3 is equal to R2 minus of minus 1 by times minus 1 by 10 times R2. Okay, then I will get an equivalent matrix as an upper triangular matrix. See, that is 1, 2, 3, 0, minus 10, minus 9, 0, 0, minus 79 by 10. See, this is an upper triangular matrix. So U, so I have AL, it is given. So let us use the pivot formula to find the determinant. So A is equal to LU, since determinant A is equal to determinant of L into determinant of U. Okay, so which gives the product of pivots, which is 79. So this is about the pivot formula. It is very easy to find the determinant. Just we have to reduce. Suppose if the lower triangular matrix will not be given, in that case we have to find first the product of two triangular matrix. That is, we have to reduce the matrix A to a product of triangular matrices through LU factorization. I will show you the LU factorization at the end. Moving on to the second formula, which is very important, known as the big formula. So here in the big formula, the permutation matrix plays a very important role, and the column orders of the permutation matrix. So in the last session, we have discussed about the permutation matrix. As we know, if we have a permutation matrix of order 2, okay, so permutation matrix is nothing but an identity matrix, but the place of ones will be different in permutation matrices after permuting the elements. Okay, so for n is equal to 2, that means if we have a second order identity matrix, then how many permutation matrices will get 2 factorial, that is 2. For n is equal to 3, 3 factorial permutations, that is 6. For n is equal to 4, 4 factorial permutation, which is equal to 24 permutation matrices. Similarly, for n is equal to 5, 5 factorial, that is 120 permutation matrices will get. So here the ones will take the positions in different ways, that is in how many ways? 6 ways, 24 ways, 120 ways respectively. So what is this big formula says? Determinant of A is equal to summation of determinant of P times A1 alpha, A2 beta, and so on, ANW, where the suffixes alpha, beta, gamma, and so on W, alpha, beta, gamma, and so on W represent the column orders of permutation matrix. So in one such example, I have shown how we can change the column order to find the permutation matrices. So we can follow the cyclic order, or we can follow the exchange of rows to get the equivalent the permutation matrices. So it is a very simple formula. So just if we find the column orders of the permutation matrix for the given size, then we can find its determinant. Remember the formula: determinant of A is equal to summation of determinant of P times A1 alpha, A2 beta, and so on, ANW, where alpha, beta, gamma, and so on W represents the column orders of permutation matrix. I will take one example to find the determinant using the big formula. Let A is equal to 1, 2, 3, 4, minus 2, 3, 2, 5, minus 1, where the order of this matrix is 3. This is a 3 cross 3 matrix. So n is equal to 3 we can consider. So therefore, how many permutation matrices will get 3 factorial, that is 6 permutation matrices we will have with column order alpha, beta, and gamma. Since it is of order 3, so we have the 6 permutations. So let us find the permutation matrices. Okay, so here it is enough to write the column orders and the permutation matrices. Here I have not written the permutation matrix, just I have written the column order and I have written the determinants, but you have to mention the permutation matrices. See, here I have shown one more column orders in the cyclic order, in the cyclic way. See, P1, 1, 2, 3 I have written, and just I have scratched this. You can follow this also, no problem, because not more than 6 permutations we can make, right? So P1 is 1, 2, 3. The place of ones in the first permutation matrix is 1 in the first row, okay? The place of 1 in the second row is 2, and the place of 1 in the third row is 3. So the column order is 1, 2 and 3. Is it clear? Okay, column order 1, 2, 3. P2, 2, 3, 1 I have written. 2, 3, I just followed the cyclic order. After 1, it is 2. After 2, it is 3. After 3, it is 1. With reference to P1, I have written P2 in cyclic way. As you know in algebra, if we want to expand a plus b plus c whole square, we follow the cyclic order to write the formula a square plus b square plus c square plus 2ab plus 2bc plus 2ca. I just followed that cyclic order. So 1, 2, 3 I have written the column order. To write the second permutation matrix, I have written the order as 2, 3, 1 because just with reference to P1. So 1 after 1, 2, after 2, 3, after 3, 1. Then P3. With reference to P2, I have written P3, after 2, 3, after 3, 1, after 1, 2. Then I have written P4. So P4, I have written the reverse of P1. It is 1, 2, 3, I have taken the reverse of P1, 3, 2, 1. Then I followed the cyclic order to write other two permutation matrices, that is P5 and P6. That is 3 after 3, it is 1, after 2, it is 3, after 1, it is 2. Similarly, P6, after 1, 2, after 3, 1, after 2, it is 3. So none of the column order has been repeated, right? If you verify this with this, these two are same, but there will be a little different, okay? So write down these permutation matrices and find their determinants. So we'll get the determinant as plus 1 minus 1 plus 1 minus 1 plus 1 minus 1, okay? So here I have found the determinant of these permutation matrix. For these column orders, I have written the permutation, that is determinant of P1. So after finding the permutation matrix of order 3, now let us find the determinant of the given matrix using the big formula. Here just I have expanded the big formula because summation is for n is equal to 6. So I'll have 6 terms, that is determinant of P1, A11, A22, A33, plus with respect to column order I have to expand the determinant, okay? So determinant of P2, see with respect to this order I have expanded the determinant, okay? The P1 order 1, 2, 3, next P2 order 3, 2, 1, okay? 3, 2, 1, I have shown 3, 2, 1, okay? 3, 2, 1. Sorry, 3, 1, 2, 3, 1, 2, 3, 1, 2. The P3 order is 2, 3, 1. Okay. Determinant of P4 times. See, the suffix A1, A2, A3 remains same. Okay. Then after A1, 1, next one will be the column order. Okay. So 1, 3, 2 is the column order of P4. The determinant of P5. 1, 2, 3. Then 2, 1, 3 is the column order of P5. Then 3, 2, 1 is the column order of P6. Just what I have to do is I have to substitute. That's all. Okay. So A11, A22, A33 represents the entries of A1. So all these A's represents the entries of A. Okay. So carefully we have to substitute the entries of A1. So with respect to the column order, so determinant of P1 into entries I have written with respect to the column order, determinant P2 and entries of A with respect to the column order of P2 I have written. So these entries are nothing but the entries of the given matrix. See here, I have substituted all the entries, finally computing or finding the value which gives the required value of the determinant as 79. Since it is a 3 cross 3 determinant, we know how to expand this determinant, but here we have to expand this determinant using big formula only. So by big formula we have got the determinant value as 79. So I'll take up a few more examples from your prescribed textbook, Gilbert Strang. Later I'll come to the problems. So let us moving on to the next formula, which is cofactor formula. So this is very important formula. As we know, we are already while defining the determinant, I have used this definition only to expand the determinant. So 2 cross 2, 3 cross 3. So to expand the determinant, we consider the cofactor formula only. Okay. So how to find the cofactors of all the entries of A, then how to find its determinant? That is the question. Okay. If it is a 2 cross 2 and 3 cross 3, nothing to worry. If it is of higher order, then little bit carefully we have to expand the determinant. So already we are all familiar with the cofactor formula. Now let us study one more time. So here I have considered the square matrix of order 3 in general. It is in the form A11, A12, A13, A21, A22, A23, A31, A32, A33. So what I'll do is I'll expand this determinant using the big formula by keeping the same column order. What I have considered the column order for the previous problem, here I will consider the same column order to expand this big formula. I have expanded the determinant using the big formula. Here I will just group the terms. I'll use simple algebra by grouping the terms. Okay, I'll just group the terms of the first elements of the I will group the terms with reference to the elements of the first rows A11, A12 and A13. I have grouped. Okay, then I have mentioned the terms of the parenthesis by cofactors. So these we call as the cofactors of the entries of the first row A11, A12, A13. Okay, so if we represent this in the matrix or in the determinants, okay, because this I can say the expansion. So next comes is the determinant. Now I'll represent all these terms in determinants. So which is A1 will be here. Wherever we have the terms, I will just place all these terms to their place. So I will get these determinants. Okay. So where this thing is represented by M11 called the minor submatrix. Okay. See how if we place these terms in the form of a determinant, it will take up in this form. Okay. Already we are all knowing this. Next, here the three quantities which already I told you represented in the parenthesis are called the cofactors. Okay, cofactors. So these are all called the cofactors of the elements A11, A12, A13. I have told this. So in this example, the cofactors are 2 cross 2 determinants. So what is the cofactor of A11? That is the term which is or the quantities which is represented in the parenthesis are called the cofactors. So we represent the cofactors by C1 because these are the cofactors of the first row. Hence we represent it by C11, C12 and C13. So therefore the cofactors are, the cofactor of A11 is C11 is equal to A22 A33 minus A23 A31 A32. Cofactor of A12 is C12 A23 A31 minus C21 A33. And the cofactor of A13 is C13 is equal to A21 A33 minus A22 A31. So the matrix with cofactor entry is called as the minors. Okay. So the cofactors are nothing but the determinant of minors. So C12 is determinant of the minors. The minors are represented by capital M. So it is of cofactor of the second element of this first row. So it is represented by M12, that is equal to A21 A33 minus A23 31. Okay. If I expand this determinant, here I have highlighted this if I expand this, how will expand? Product of the elements along the principal diagonal minus along non-principal diagonal, isn't it? The difference gives the value of the 2 cross 2 determinant. So here the determinant of that minor gives A21 A33 minus A23 A31. But what is C12? It is reverse of this M12. So what I can say is determinant of M12 is this, but the cofactor C12 is the reverse. So which is same as negative times of determinant of M12. So with these all, here we can define the cofactor formula as Cij is equal to, okay, I represent the element in the first row, I represent the element of the ith row, J represent the element of the jth row. So Cij is equal to minus 1 to the power I plus j times determinant of Mij. Because here the sign is important. So for some factor will get plus and some factor will get minus sign. So this sign is very much important to find the cofactors of each and every element of the matrix A. Okay, so using this formula, so we can define the determinant as determinant of A is equal to AI1 CI1 plus AI2 CI2 plus and so on plus AIN CIN. So once if we know the cofactors, then we can find its determinant by following the sign minus 1 to the power I plus j. Let me consider one such example. Already we know how to expand the determinant 2 cross 2 and 3 cross 3. Here I have taken a 4 cross 4 determinant. Okay. Let us apply the cofactor formula to expand this 4 cross 4 determinant. Okay. So expanding with reference to only the first row. So determinant, because determinant of A is equal to A11, since we have the 4 elements in the first row, so the entries are A11 into the cofactor of the first element plus A12 cofactor of the second element with reference to the first row, okay, plus A13 into cofactor of the third element plus A14 cofactor of the fourth element. Since here the third and fourth element are zeros, so hence the determinant will reduce us to only the 2 elements, that is determinant of A is equal to A11 C11 plus A12 C13. Okay, alright. Now let us find the cofactors. So with the help of the cofactor formula, Cij is equal to minus 1 to the power I plus j times determinant of Mij. Okay, so here I is equal to 1, j is equal to 1. First element in the first row and first column, right? So that is the cofactor C11 is equal to minus 1 to the power 1 plus 1 determinant of M11. Minus 1 to the power 1 plus 1 is plus 1, so it is same as determinant M11. C12 is equal to minus 1 to the power 1 plus 2 determinant of M12, which is equal to minus, because minus 1 to the power 3 is minus, so minus determinant of M12. So let us find the minors. Minus M11. How the minors we will get? So what we have to do is, so to find the minus, see we are finding the cofactor of, I will show you, cofactor of this entry. Okay, first element, cofactor of first element. So the sign we have to follow is plus. Okay, next minus, next plus, next sign minus. This will continue. Okay, if you want to get the cofactors of other, then we have to follow the sign minus, plus, minus, plus. It will go in the cyclic way, plus minus, plus minus, plus minus. Okay, since the third and fourth entries are 0, so just you have to get the C11 and C12. Okay, so to get the cofactor of 2, I want the minus. Okay, that is determinant of M11. So to consider the minor matrix, so what I have to do is I have to leave where this element will be located in the first row and the first column. So I have to leave the first row and first column to write the minor. This is the minor matrix of 2. Okay, so determinant of this minor is M11, which is equal to determinant of, I have written here, here I have written M11, which is equal to 2 minus 1 0 minus 1 2 minus 1 0 minus 1 2. So this minor I've got by deleting the first row and first column of the first element. Similarly, this matrix, minor matrix M12, we will get by deleting where this second element will be located in the first row and second column. Okay, first row and second column. So to consider the minor matrix of this cofactor entry minus 1, now I have to delete this row and this column. Okay, the remaining are the minors, the remaining elements 3 cross 3 is the minor of M12. Am I right? Now let us get the minus. So I have got the minus M11 and M12. Let us find their determinants. Since it is again a 3 cross 3. Okay. So it is again a 3 cross 3. So M11, to find the determinant of M11 and M12, now I have to again consider the cofactors. Right. Okay. So let us denote M11 by the matrix B. So matrix B is equal to 2 minus 1 0 minus 1 2 minus 1 0 minus 1 2. So let us find the determinant of B using the cofactor formula. Okay, B11 into C11 dash. C11 dash are the cofactors of first element of the matrix B plus B12 into cofactor of the second element. The third element is 0, nothing to worry. Okay, so let us find the cofactors. C11 dash, again the same formula we have to use. Okay, minus 1 to the power 1 plus 1 into determinant of, with respect to the matrix B, so I have represented the suffix as B, don't confuse with the above matrix. C12 dash, that is equal to minus 1 to the power 1 plus 2 determinant of the minor of the second element, that is MB12. Okay, so determinant of B is equal to 2 times 2 into, okay, formula B11 into cofactor of first element, that is plus sign, with plus sign determinant of MB1. Determinant is obtained by deleting the first row and the first column, that is 2 minus 1 minus 1 2. Okay, so the next sign is minus. Okay, because this gives minus sign, right? So minus of B12 into determinant of this second minor MB12, that is, this determinant will obtain by deleting the first row and the second column. Okay, so simplifying this, which gives the value of the minor M11. Okay, expanding and simplifying gives 4. So determinant of B is nothing but the determinant of M11, that is 4. So in the same way, so let us find the determinant of M12. Let us represent this minor of the matrix by C. Okay, in the same manner, we will expand using the cofactor formula. Okay, then which gives determinant of C is equal to determinant of M12, which is equal to minus into minor of MC11 minus here this minus, okay, C12 minus 1 into determinant of C12. So now expanding this, we'll get the value as minus 3. Now substituting 2, 3 and 4 in 1. So substituting the values of M11 and M12 in the formula 1, so gives the determinant of A as 5. So strictly we have to follow the cofactor formula to find the determinant. Okay. So in the next example, here I have a 3 cross 3 matrix. Okay, you follow the same cofactor formula and expand. One more example I have taken. Some 3 examples I have taken. So this is about the permutations and cofactors and a few important formulae. Okay,